Welcome back to the Art of Math. Today we're going to be wrapping up our Algebra Applications section and going over the question of, is the square root of 2 rational? A.k.a. deadly mathematics, Hippasus versus the Pythagoreans. I apologize if I'm not saying that name correctly. Okay, so let's go a little bit into the backstory. So math can be deadly and dangerous. So the dangers of math, Hippasus and the Pythagoreans. There was a school of ancient Greeks known as the Pythagoreans, followers of Pythagoras, and rumor has it, and I encourage you guys to read Wikipedia or other sources, study this more. This might be a fake story, but there's a famous myth that Hippasus, one of the former members of the school, divulged a secret, and because he had divulged it about the square root of 2, they had killed him. So that's why there's that in the title. And just for fun, math has a pretty colorful history. So, a lot of you folks might not, might think of math as this like really stuffy thing you just do on a piece of paper. So I'll just mention there were math duels in Italy in the 16th century, and you might want to check those out. So those are pretty fun and funny. So basically somebody would say, hey, here's an equation. I challenge you to solve it. And if that guy could solve it, then, well, at that time it was mostly guys. So if that person could solve it, then they would come back and give them another challenge. So I can solve this, but can you solve this? And so these would be sort of like duels, and these techniques would be top secret, because if someone found out your technique, then you would be sort of out of business. All right, so that's a little bit of a backstory. So for this video, we have, is the square root of 2 rational? So first let's go into what is a rational number. It's pretty straightforward. It is just p over q, where p and q are integers and q does not equal 0. So you could think of it basically as a fraction with nice numbers. So some examples might be 3/4, -5, because -5 you can write as -5 over 1, 0, which is 0 over 1, 0.23 would be 23 over 100, even repeating decimals like 0.33333 or 0.3 with a bar would be 1/3. So all of those you can express this way. However, there might be some numbers that you cannot express this way. And so one of the questions you might ask is, who cares, right? Like why does this even come up like in a normal situation? So the Pythagoreans were studying a pretty, so I want to convince you guys that this is a natural question to ask. So let's say you're one of these Pythagoreans and you're obsessed with numbers and geometry, and you're studying this fairly simple case where there's a right triangle, meaning this is 90 degrees, and it's just 1 by 1. So you want to know, if this is 1 and that's 1, what's the measurement of this third side? Quick tangent. So in later videos in this series, we're going to go into the Pythagorean theorem, which discusses how you find this number exactly, which would be this side squared plus that side squared, giving you that side squared. So a squared plus b squared equals c squared. But like I said, we're going to go into that into detail later. But that's just to show you that this is going to relate. So, and actually, the Pythagoreans didn't even have the notion of a square root. So they literally thought of these as squares. So when you saw a squared, it was this side extended to be a square that's 1 by 1. That will be its own square, whatever this is, and whatever that is would be another square. It doesn't quite look like a square in my diagram, but these should all be squares. So this should be a little longer. So the point is, can we find a nice number for this dimension such that this area plus that area is that area? Now, we know if this is 1 by 1 and that's 1 by 1, the area of a square is just the number 1 times 1 squared for this square, so that would be 1 plus 1 is 2. So therefore the area of this square needs to be 2. So can you find a number such that that number squared gets you 2? Which is the same thing as saying, is there a number that's the square root of 2 that is a nice number, that's rational? Now, you might think like, well, let's just say it's 1.5. I know 1.5 doesn't quite work, but let's just imagine it is, and that way you guys can see why we even care about these rational numbers. So if this were 1.5, so we'd have 1, 1, 1.5, you could just rescale all these numbers, basically double everything, and then you get 2, 2, and 3. So you get integers, nice whole numbers over here. So the idea is the rational numbers can easily be converted to an even simpler set of just whole numbers in this case, integers in general. So maybe this answer is like 1.4278, whatever. But then we could scale that up. So we want to know, is there something that will ultimately get us nice numbers here? And we're going to find that that's not really the case. But before we go there, so the point is, I really just want to stress, this is a natural question to ask. This is not like a math nerd sort of question. If you're just, you built a triangle, this is 1 by 1, you might have a farm field, whatever, and you want to know, like, what is this measurement? Is this 1.5? Is it 1.4? Like, I hope it's not too ugly. So you might be genuinely curious about that. All right. So let's go into a little bit of a fun fact. This, not a lot of people know this. So I was reading this book, which I really recommend to anybody interested in synesthesia. So Pythagoras may have had synesthesia. So what is synesthesia? That's, for those of you that don't know, it's when you have a crossing of senses. So for example, you might hear a sound and see a color, or you may see a color and hear a sound. You can, maybe when you touch something, you feel a taste on your tongue. It can be all sorts of weird things. So I say weird as in unusual, not in the sense that there's something bad about it. So if you're interested in studying this further, so for example, you may have heard a lot of like famous music composers or writers had synesthesia. So if you're really interested in this, I highly recommend this book. Wednesday is Indigo Blue, and it basically tells you about all the different types of synesthesia and anything you pretty much, for the normal person, anything you've wanted to know. So there's a conjecture in the book that Pythagoras may have had a form of synesthesia. This will be a mouthful, but specifically ordinal linguistic personification. So what does that mean in human terms? It just means that when he saw numbers, they had genders, male and female. So for example, 1 is male, 2 is female, 3 is male. And you might think like maybe 1 because it's sort of straight and 2 is like more curvy. So like 6 and 8 are sort of more curvy. So that might make some sense. But anyway, it's not like he made this up. So if the claim is true that he had this, that means people with synesthesia don't make this up. It's not like, oh, you know, I think of 1 as a male. No, it's, you literally cannot help but associate something. So it's automatic. As soon as you see the number 413, you immediately think of male or whatever it is that you think about. All right. And by the way, I know someone that has this. So this is a very real thing. And according to the book, the estimates aren't super clear, but roughly 1 in 23 people actually has synesthesia. All right, so I highly encourage you guys to look into that. And that might, by the way, it's like, why am I bringing this up? Because this obsession with numbers and nice numbers, rational numbers, irrational numbers, is often attributed to just the wacky Pythagoreans, how they were just like this cult obsessed with weird numbers, and if you didn't like their numbers or geometries, you got killed. That may be overblown. So Wikipedia actually doesn't think, well, at least in Wikipedia doesn't seem to think that this is true, because they're saying that it's rare, it's 1 in 23 people, and since this was a consistent sort of belief among the Pythagoreans, it probably wasn't synesthesia, because synesthesia is not a belief, it's an experience. I tend to disagree, because I think all it takes is one person that may have experienced this, such as Pythagoras or any one of their leaders, and the others might have not even known why they were going along with it. For them, it might have been a spiritual thing. They might have just thought that, oh, well, I guess, you know, 1 is sacred, 1 is male, 2 is female, 3 is male, 4, whatever. So I tend to go with the theory that this is just a cult with one real synesthete, person with synesthesia, instead of saying that all of them just had these mystical beliefs. So I don't know that a lot of people know this. I really want to like kind of bring this to the forefront and help get the conversation going about this. All right, enough background, but hopefully you guys are kind of getting into the backstory, the history. All right, so here, let's get straight into the meat and potatoes. So the proof. let's assume the square root of 2 is rational. So what does that mean from before? It means we can write it as p over q, where these are integers. Now I'm going to make one little additional assumption that p over q is in simplest form. So for example, it's not 6 over 4, it's 3 over 2. So let's set it up. So square root of 2 is equal to p over q. We're going to use our algebra knowledge to square both sides. So we have 2 is equal to p squared over q squared. Now we're just going to move the q squared over. So we have 2q squared equals p squared. Now I put a box around this because this is the critical step. It doesn't look like much, but I want you guys to come back to here if you get lost and think about what this means. Look at the left side. The left side has 2q squared. So this is 2 times some integers, so therefore the left side is even. So if the left side is even and we're squaring some other integer, that means p must be even. So that's our first little conclusion. So if the left side is even, the only way to get the right side to be even is to have p be even. So that's this part. Now, since the right side is even, it can't just be divisible by 2 because we're squaring some even thing. So that's going to pop out 2 2's. So that's going to give us a 4. So therefore the right side is divisible not just by 2 but by 4. At least 4. It could be more. So now we come back to this and say, well, the right side is divisible by 4, but there's only 1 2 here, so there must be at least another 2 coming from this q squared. So we're kind of running this logic again. So therefore, if q squared has a 2 in it, that's even. But you can't just get 1 2 because q is an integer, so far we're here. So q must be even. So now, if q is even and we square q, we're going to get 2 sets of even numbers, right? So that's going to give us, and so we don't even need to continue there. So we could stop right there. As soon as we realize that q must be even, so again, let me retrace that. So we started with the left side must be even because of this 2. So the right side must be even. So p must be even. But if p is even and we're squaring an even number, we pop out 2 numbers that are even. So that gives us a 4 because 2 times 2. So now that 4 on the right has to be compared with this 2. So another 2 has to be coming from somewhere, which has to be from this q squared. So the only way q squared can get you a 2 is if each of the q's is even. And that's where we can stop. Because now we've proven that p must be even, so basically this is even, and q must be even. But check this out, p over q we've assumed is in simplest form, but if they're both even, that can't possibly be in simplest form. So for example, 6 over 4 is not in simplest form. So since it's not in simplest form, the 3 dots mean therefore, that's just math notation, shorthand. That means our assumption was wrong. So this is a proof by contradiction. We assumed something, our assumption led to nonsense, and therefore we conclude that our assumption was wrong. So these 2 arrows facing each other, kind of like bulls locking horns, indicate a contradiction. So therefore the square root of 2 is irrational. There are no 2 numbers like 17 over 4 or whatever, or over 9, that you could find that will get you to be square root of 2. Now you can get very close by taking larger and larger fractions of like closer numbers, but you'll never exactly nail it. So that's what we've shown in this proof. All right, now just to relate it, if you could sort of say, but you know what, okay, so we messed up once, but what if we'll reduce it now, so it wasn't in simplest form, but we'll divide both by 2 and now they are. Well, we can just run this again. So this is going to basically give us an infinite descent. So if we think we found something, we're just going to keep shrinking it and infinitely shrinking it till forever. So we're never going to find it. There's a mathematician, Fermat, spelled F-E-R-M-A-T, and he's also very well known for this method of infinite descent. So that's kind of the logic we're doing here. All right, so that's the proof. 2 more things I want to leave you guys with. First thing is, for those of you that found this to be pretty cool and just want to really solidify your knowledge, here's a practice or challenge problem, which is try to do the same thing, but not for 2, but for 5, or you could try 3, or any other non-perfect square. So prove that the square root of 5 is irrational as well. This will just get you practice so you can get comfortable with this technique. Finally, a really great follow-up video for this would be on the YouTube channel V Hart. Many of you might have already heard of her. She has wonderful videos with a lot of really great visual stuff mixed with maths. It's like math presented in a visual manner. Very, very awesome stuff. So check out her video, What Was Up with Pythagoras. So that's basically gonna go over everything we've gone over here, but she does a much better job than I could ever do in terms of visually presenting this in a kind of a fun way. So I think if you watch that video after this one, or it doesn't matter which order, you'll have a stronger foundation. All right, I'll see you guys in the next video.